Good afternoon to everyone and good morning to some others in different time zones. This is Simon Boyce with ARMS Reliability. Thanks for joining our RCM Best Practices Making Quantifiable Decisions webinar today. I'm going to introduce ARMS Reliability Engineering Manager Jason Ballantyne here in a second, who will take you through today's webinar that should last around 40 minutes in length. You will find you can ask some questions to us by clicking on the chat box in your menu and typing in a question. You can either send that directly to the presenter or you can send it to everyone. So we will try to monitor that, but and answer those as best we can. If we don't get to them, we'll send you an email after the webinar with the answer to that question. Without further ado, I'll introduce Jason. Jason has been with ARMS Reliability for a little over 10 years now, mainly based in North America, working on a variety of projects including maintenance strategy development, maintenance strategy optimization, system availability and capacity, criticality, and also leading our root cause analysis program. So today, Jason will take us through some RCM best practices, show you probably at the end a little bit of some of the tools that we use to help make quantifiable decisions, and we hope you find it worthwhile. Without further ado, I'll turn it over to Jason.
Thank you, Simon. So today we're going to be not so focused on RCM and how to do RCM, but more about how do we actually make the decisions that follow the RCM methodology, and how do we quantify those decisions that we make. So let's get started. So the first thing we're going to do here is look at, well, what is RCM and what do we mean when we use the term RCM? And what we're really talking about here is the quite basic kind of look at it, which is the first step is a failure mode and effects analysis. So we're going to start by identifying the maintainable item, which in this simple example is a lawnmower, followed by the function, functional failure, and all the failure modes. And this is really designed to explore all the possible ways that we can fail to perform this particular maintainable item's function. And that's really what we're trying to do with the failure mode and effects analysis. Now, further to that, we need to define what the failure consequences are in the current operating context. And that's really important when we're doing RCM and also doing FMEA, that we understand what that current operational context is. And the value of doing that and adding the failure consequence is that we fully understand just how important each of the failure modes are. And that's going to help us when we look to try and quantify and select our particular maintenance tasks. So the first step that we need to think about once we've defined all of our failure modes is to try and understand the actual failure behavior that's occurring. Because until we understand what the failure behavior is, we really can't begin to even look at what maintenance tasks are even applicable, let alone starting to try and quantify which is the best maintenance task to choose. One of the steps in the RCM process is to define the applicable task and to define whether it's worth doing. And we're going to go through both of those aspects of that question in our webinar today. So the first one we're going to look at is the task applicable? And that's what we're going to focus on here. So the first thing we need to realize is that not everything fails the same way. Some things fail according to an infant mortality type behavior, where we have a high probability of failure early on in the life, and as we proceed through the life of that particular maintainable item or failure mode, our probability of failure actually decreases. Now, if we have this type of failure behavior, we're a little limited in the maintenance options that we actually have. We can't choose to do fixed time maintenance because that would simply increase the probability of failure and increase the cost and not really provide us with any value and actually do more harm than good. We could do some inspection activities, but again, it's not really going to add a whole lot of value, and we've still got this early life failure occurring. So options here are to do more of a root cause analysis approach, maybe a redesign, and really try and understand why we are having an infant mortality failure on something that we really don't think should behave like that. But this is a failure mode that we need to consider and identify, because it is important that we don't select the wrong maintenance tasks. Now, the second behavior that we're going to look at is when we have those random failures. These are the failures caused by human error, variable service conditions, and these are ones where our probability of failure doesn't actually change over time. So even if I have a new component, it has the same likelihood that it's going to fail as a component that's been installed for many years. And this is hard to sometimes get our head around. What is a true random failure? We've got to kind of think of it as though if I replaced the component today, I really wouldn't be in any better position tomorrow than I was today. And the example I often give in my training courses is a transformer being struck by lightning. It has the same probability of being struck by lightning, whether it's a brand new transformer or whether it's a transformer that's 20 years old. So that's a true random failure. Now, for this type of failure behavior, we do have some maintenance options. We can't do a fixed time replacement. That doesn't add any value. But we can do some kind of inspection or condition-based maintenance, provided that there is a degradation mechanism that we're looking for. If we can't find that degradation mechanism, we have to look at our other options, which are the run to fail. Maybe we need to add some redundancy to try and mitigate the effect of this particular event occurring. The next behavior we're going to look at is when we have the steady aging. These are typical of corrosion type failures, maybe refractory life, things where the probability of failure increases linearly as compared to the time scale there. Regular inspection is a good option here, and also time-based restoration and replacements. Now, the final behavior we're going to look at is a wear-out type failure. And this is a really good one if we see this type of a behavior. This means we have a predictable end of life of our component, which gives us lots of options. We can now do time-based replacements. We can do inspections. We can always let it run to fail. But it is a good failure behavior in that we truly understand when the failures will occur, and we can try and achieve most of the life out of the component before we actually need to do the replacement event. Now, the one situation where this wouldn't be such a good option is if all of these were occurring before the design life, and that's something else we need to consider. Right now, we're just focused on the actual failure behaviors. And everything we've talked about up until now has just been failure behavior. We haven't talked about how often it occurs. We haven't talked about how often we need to do those maintenance activities. It's purely just been about what maintenance tasks are applicable to particular failure behaviors that we might see. So we do have our RCM decision tree, and our RCM decision tree, we can start a number of places. We're going to start this one by saying, is there any health, safety, environment, or operational risks? And if there's not, an applicable task, and the task that we probably should be choosing, is to just let it run to fail and behave reactively and just fix it when it breaks, because there's no impact if we do allow it to run to failure. Now, if there is any kind of risk, we need to look at, is there any kind of a condition monitoring or inspection type activity that we can do? And if there is, we should be defining that particular activity. We also look at, is there any type of failure pattern here? Is it a predictable end of life, in which case we can do a fixed time replacement? If we can't find that deteriorating mechanism and it's not a wear-out failure, well, then we fall back to the redesign option there. Now, this decision tree is built so that we always look for the predictive activity first, but that's not always going to be the most cost-effective option when we start to try and quantify the different maintenance activities. So we need to be able to evaluate both the predictive and the preventive activities to find the right activity for our actual application. So decision tree is a good basis for what we're doing, but we need to be working on evaluating the maintenance tasks. And we're talking about evaluating, we're talking about quantifying and selecting the applicable maintenance activity. We need to do a balance. We need to do this balance between understanding what our business goals are, understanding what our cost of failure is, and doing just enough maintenance to meet the objectives of our business goal and try and reduce that cost of failure. So we're not just purely doing a balance between the maintenance cost if we did it on a breakdown and the maintenance cost if we do it planned. We're not doing that. We're doing the total business benefit balance between production losses, losses in availability, statutory, environmental type risks, any quality or efficiency losses we may see, and maintenance budget. And that's on one side of the balance here. On the other side of the balance is our maintenance task and any consequences associated with doing planned maintenance tasks. And often there isn't many because we schedule to do this work during normal outages. We do it, schedule to do the work, and it's set in our budget early on in the year, so we don't need to consider a lot of those losses, provided we can do them in the defined windows. But this is really the balance we need to do. We're trying to find this optimal point between under-maintaining and having failure events, and over-maintaining when we're doing too much maintenance and that costing us too much. We're not trying to just do more maintenance. That's not the answer here. We just need to do just enough maintenance to meet our business goal, because that will be the point at which our optimal maintenance interval is achieved, and we're able to justify and quantify the value of all those maintenance activities. So I'm going to start with an equation, and I've threw this equation in here because we need to illustrate a point here that we do have an equation for reliability. Reliability equals e to the minus lambda t that will help us determine the reliability at any point in time. The problem is, though, that we can't use this equation to try and help us determine when to do maintenance tasks. And the reason we can't do it is because the probability of failure is not always the same over time. So we talked about those failure behaviors already. Not everything fails randomly. We do have this infant mortality type failures. We do have random failures, which this would apply to, but we're kind of limited on our maintenance options. But then we also have those wear out type failure behaviors. So we have things wear in and we have things that wear out. And for that reason, this isn't the right equation to be using if we're trying to determine how often we need to do maintenance tasks. To determine how often we need to do maintenance tasks, we need to use a Weibull distribution. And some of you may be familiar with this Weibull distribution. This is the simplified two-parameter Weibull distribution here. Now, this particular equation will allow us to define what the failure behavior is, and also define what the interval is, to allow us to calculate what the reliability is at any point in time, and help us determine how often I need to do my maintenance task. So there's a few other parameters here we need to look at, and you'll see there's some new parameters we're introducing here for those that aren't familiar with this equation. One is the eta value, known as the characteristic life. This is actually the point at which 63.2% of a population will go into a failed state. So we can think of this as how long does the item last, and we can approximate it like that. The second new parameter there is the beta value, or known as the shape parameter. Now that's a really easy one to translate, because that tells us which of those failure behaviors we're actually experiencing on this failure mode. If my beta value is less than 1, it means I have an infant mortality failure. I have that early life failure event. If that beta equals 1, I have a random failure, which is the probability remains constant throughout the life. And if that beta value is greater than 1, it means I have that wear out, or that predictability in terms of where my end of life of my component is. Now, the other benefit of this particular equation is its simplicity, in that I can talk about how often something lasts, I can talk about how it behaves, and I can translate that into parameters that I can then use to calculate reliability. I'm not having to talk about standard deviations. I'm not having to talk about mean, medians, normal, log normal distributions. I'm not having to have that conversation. I'm having a very practical conversation about how often does it last, what's the failure behavior. And that's what we want to be getting to, because we're communicating this to our mechanics, to our electricians. We're not always doing a statistical type analysis here. We're doing this to make practical maintenance decisions, and that's what we need to keep in mind. So we have some options. We have a preventive maintenance task, and for our preventive maintenance task, there's certain things that we need to define along with that particular activity. The first thing is we need to define the task duration. So you can see here that I've got 12 hours on my task duration. We also need to define, well, how many people do I need to respond and do this particular activity? So I need 2 mechanics and I need 2 new ball bearings here to go along with that. Now, this curve you see here, we're going to explain this in a little more detail as we proceed, but what this is this is helping me determine when the best time to do this particular maintenance task is. And this is where we start to differentiate and go away from doing things in Excel and being able to do things in a dedicated software tool where we can do simulation that helps us calculate when the best time to do these maintenance tasks are. So this is a fixed time activity here. We also need to talk about inspections because that's an essential element, an essential part of any maintenance strategy we develop is our condition-based maintenance programs. And when just setting up those programs, one of the most important things to consider is what the PF interval is, or what the time is between when the potential failure is detectable and when it actually functionally fails. Now, that P2F interval is going to vary based on the type of inspection I'm doing, because remember it says when the potential failure becomes detectable, which is going to be different if I'm simply doing a look, listen, and feel inspection. It's going to be very different and a lot longer if I'm doing a detailed vibration analysis. So as I do my different technologies, I get a different PF interval, and that's the most important thing. This is not related to mean time between failure. This is not related to the Weibull distribution. This is purely related to the type of technology you're using to do the inspection. And there's definitely some easy optimization wins that you can get just by considering what your P2F interval is, and then look at how often you're doing the task. If you're not doing the maintenance activity currently at the PF interval or less, you will be missing potential failures, and you need to recognize that fact and say we're going to have some failures we're not going to pick up as a result of our programs here. So I've put a couple curves on a couple different technologies here, and you can see how they change the PF interval as we use more advanced techniques. So if we look at our inspection, yes, we have to define that P2F interval, but we also have to define how long does it take, and here we're going to take half an hour. And we also have to define who does the maintenance activity, and we get a similar looking curve here. And this curve, again, is looking at what's that balance point? At what point should I actually do this maintenance task, and what happens if I deviate from that optimal point? So if we look at this on assessing the intervals, we could look at the cost of this if we did it at an 18-month time period. And my cost, if I did that PM activity, would be $8,311. You may say, well, that's great. That's actually saving me a lot of money over just letting it run to fail, and I'm quite happy with that. But maybe there's an inspection activity that's actually a lot better. And doing this condition-based maintenance, I can get my cost down, in this case, to $4,938. So I've actually almost halved my cost that I had comparing my fixed time maintenance activity to my inspection activity. And some of you may be thinking, well, of course, condition-based maintenance is always good. We just got to do an inspection. Well, the clever thing with this is that I'm not just doing the inspection activity. Incorporated in that cost number there is actually the cost to do 1.7 secondary actions, and that's defined by my Weibull distribution. So I'm budgeting not only for doing the primary activities, which is the inspections, but I'm also going to budget for doing a secondary action, which is the replacement. So we'll talk a little bit more about budgeting a little later in this webinar. But all you understand here is this type of ability to quantify maintenance activities is going to be great if you're trying to put in new condition monitoring programs. You can show the value. If you're trying to justify fixed time replacements because that's the only option you've got information to be able to justify that. And if you've got the information in a format that is in line with those business goals, which is the financial side of things. Now you can see some other elements in the window there. We could see safety criticality, operational criticality, environmental criticality. Those are 3 other elements that we can define the value of a maintenance activity. We don't necessarily put financial values on safety, operational, environmental criticalities, but rather we put a severity value on those and look at those as though they're a reduction in risk that we're going to see. And we can plot and we can do a whole bunch of things at the end of this to look at what's our residual risk once we've defined what all our maintenance activities are going to be. But we need to be able to assess the alternatives in a simulated environment to enable us to justify what tasks we're recommending to be done. Now, a little more on this optimization curve and those little curves you saw for the plan task and the inspection activity. And what this curve was actually showing us, if we look at it in more detail, is to the left of this curve is where we were doing too much maintenance. We're doing too much maintenance because we're doing the task very frequently, and our cost was quite high as a result of that. As we do the task less frequently, our cost starts to come down and we reach this optimal maintenance interval in the middle here, which is this low point. Now, as I progress further and I do that maintenance task less frequently again, we start to not do enough maintenance and we start to have some failure events starting to occur within our system. So we're trying to find that perfect balance point, but we're also doing it in a way that provides the engineer with a lot of information to be able to make an informed decision. This is not black box work we're doing here. If we want to adjust the interval, we know what the benefit is, whether we adjust the interval to the left and do it more frequently, or we adjust the interval to the right and do it less frequently. If I was just to look at these and I look at the optimal point and I compare the optimal interval to the one interval earlier or the one interval later, it looks like it's actually better, slightly better, if I actually push this interval out rather than do it more frequently. Based on my cost of downtime, based on my business goals that I'm looking at, it's better to do the task less frequently. That's the better overall decision for my business if I can't do it at the actual optimal interval. So at this point, I'm going to jump into a brief demonstration and show you how I would actually do that rather than just looking at screenshots as we have so far. So let's jump into the tool here. So what we see initially here is we see a function location drill down. This particular one is for a plastic sheet extrusion plant. I'm going to drill down to the maintainable item, which is the screw feeder. Then I'm going to define the function, functional failure, and I'm going to define the failure modes. And I can also define secondary functions, secondary functional failures, additional failure modes. So I can define all of that in a very graphical environment here. I can also copy and paste, and I can do all those kind of things. So that's not really what we're interested in today. We're interested in selecting maintenance tasks and how do we quantify the value of those maintenance tasks. So I'm going to take you through some of the data that's needed to be able to answer that question. And the first one is, well, what's the cost of downtime? And we do need to enter that, and we put that in as an effect. And this one here, we get a major loss of production. And if I was to open this up, we'd see that our major loss of production equates to $10,000 per hour. So each of these fields is customizable. I can change them. I can have all different rates in here if I choose. So I've just picked a 10,000 hours for simplicity for the example. Now, the next thing we need to do is we need to define that Weibull distribution, define how often it happens. And we've got a couple of ways we can do that. We can do that if we have real data. We can actually do an analysis of real data that determines what those Weibull sets are. But we can also have those discussions with those people that are knowledgeable about how the piece of equipment behaves and how often it fails. So this one's going to fail once every 5 years, and it's going to fail with a fairly repeatable life. So we've got a beta value of 4 in there. So that's the basic information I need. So far, I've got the cost of downtime and how often it occurs, and that's the only 2 things I've looked at so far. I need to get into my maintenance tasks, though, and I need to define those maintenance options. And the first thing I need to define is, well, what happens if I do nothing? Because that's going to become my baseline against which I'm justifying actually doing some type of proactive maintenance. So I'm going to look at the corrective task here. I'm going to replace the bearings. It's going to take 12 hours, 2 mechanics, 2 bearings. So seems simple enough. We're going to pick these from lists. People like our maintenance planners are very good at this type of stuff. They know where this information comes from, or even better, you may have some of this information in your CMMS systems. So I'm going to cancel that one. Now my other options are I could do a fixed time replacement, which we're going to call planned, or I could do a condition monitoring type activity, which we're going to call inspection. For the planned activity, I need to define things very similar as I did for the corrective task. I need to define how often it takes. You can see I've said that it's going to take me a little less time. Generally, planned tasks are more efficient than doing things on the breakdown in the middle of the night. So we're going to assume it takes us a little less time, but it still does need 2 mechanics and 2 bearings. I'm also going to define my inspection here. I'm going to carry out some vibration analysis. That's where I'm going to take half an hour. I'm going to need this technician to do that for me. And under this predictive data tab here is where I put in my P2F interval. So based on this technology, I think I'm going to get about 2 months warning time from when the failure becomes evident to when it's going to functionally fail. Now, people often say to me, well, where do you get that information? And it's a really hard one to try and determine where that comes from. We generally talk to the people actually doing the work, and ask them questions like, when you see a fault, how long should we wait until we actually do something about it? And that'll give you an idea for what the PF interval is. The other people who have a really good idea of what the PF interval is those that are currently doing inspections, currently finding deteriorating mechanisms, but really never get around to doing anything, and eventually it fails. And we call that an inspector failure. And so there you get a very good idea of what that P2F interval is. So we've defined these 3 maintenance options here: the corrective, run to fail, fix it when it breaks, planned, fixed time replacement, inspections. Now, because we have a Weibull distribution, we understand this is a wear-out type failure behavior. We know that all those tasks are potentially applicable. Maybe not so much the corrective, because we know there is a $10,000 loss associated with that. So the tasks are applicable. Now, are they worth doing, and which is the best one? How do we quantify it? And that's what we want to get to here. So we go to the strategy tab. And the first thing I want to do is I want to run a baseline. I want to say, if I just run to failure, don't do any proactive maintenance, what's going to be my cost? And we know it's going to be high because we've got some losses in there, and it actually comes out to be $3.1 million. It results in 1.7 failures over the lifetime. How do you say, well, how do I have 1.7? Well, I'm definitely going to have 1 failure in the lifetime, and I got about a 75 or 74% chance of having a second failure in the lifetime. And by default, I've set this up for a 10-year lifetime, but you can adjust that. That 1.7 failures is going to result in 313 hours. And again, you kind of think, well, how does it 313? Well, this is taking into account delays to obtain spare parts if I don't have them on site. It's taking into account delays to get people to site if they're not already there. So all those extra logistic delays can be taken into account if I choose to. I don't have to, but I can choose that. Now I need to start doing some evaluations, and I could start making some guesses here, and I could say, well, I'm going to do this every 3 years because I know it lasts 5, so let's do it every 3. Let's enable that activity, run the scenario, and we say, well, it's actually better. Like, we've made an improvement. We've gone from 3.1 million down to 657,000. So I've saved about 80% of what I was before. I'm still having some failures, though. I got a 36% chance of a failure. So maybe this isn't the best strategy. But I don't want to just guess what I'm doing here. I've put this into an environment where I can simulate it, and I can simulate it very easily. I click interval optimization, and I run this start optimization simulation. What it's going to do for me, it's going through and it's calculating the cost at a number of different intervals. And again, this is where we start to struggle to do some of this stuff if we're trying to do it in Excel. We'd have to do this over and over again. This would become quite a lengthy exercise to try and work out what this is. So it says, well, the best time to do this is at 7,728 hours, which is the low point on this curve, right here on the curve. You can also see the cost has popped up. It's going to be $30,000. If I was to accept the recommendation there and run the simulation, the best time to do this activity, if all I could do would be a fixed time replacement, is to do it at 7,728 hours, and it would cost me $30,000. You may say, Jason, you're being ridiculous. You can't do it at 7,728 hours. I can't even hardly say that. So what we're going to do instead is we're going to do this once a year. But in terms of quantifying this, I can tell you that that's actually going to cost you $21,000 more over the lifetime of this particular component by doing it at that exact annual interval. Now you may say, well, that's fine, I understand that, but I can't do it at that other interval. There's no way I can do it at 10 months. I really need to be scheduling this every 12 to fit into my turnarounds and my normal outage schedule. But at least you understand what that is and where the potential value is if you are trying to shift those things at a later time. But what I haven't evaluated here yet, I know what my cost of doing a fixed time activity is, but let's look and see what the cost of doing an inspection activity is. So I'm going to run a similar optimization, and when it runs the optimization this time, it's looking for the actual inspection activities. It's saying, if I do the inspection, how much is it going to cost me? And what it says is, based on the inspection parameters that I put in there, I need to inspect this at 1,176 hours. So once I go beyond that time frame, my cost starts to really go up very quickly. And the reason that's going up so quickly there is because I'm starting to see some failure events. I'm getting outside that P to F interval, and I'm not picking up the failures. I'm just letting it happen. So I don't want to be there on the curve. I definitely want to be in this lower part of the curve here. But I'm going to accept that recommendation, run the simulation, and my cost comes all the way down to $7,000. I started at 3.1 million. I'm now at 7,000. And the reason I'm at 7,000 is I'm doing condition-based maintenance. I'm replacing the components when they need to be replaced. I'm able to order the components in time to have them delivered to site to actually be done. It's done planned, so I don't have to call people in, don't have to pay any overtime for it. It's a much better way to do my maintenance. And maybe we all know this is the right thing to do, but here I'm actually quantifying it. I'm giving justification behind what I'm trying to drive my maintenance program to be, which is this condition-based maintenance program. So think about all those discussions you've had about trying to prove the value of condition-based maintenance. This helps you do it, but it also helps you evaluate all the other alternatives that we have, and it helps you evaluate all the other alternative intervals. So I'm just going to leave that there, and I'm going to go back to the slides here. So it's not just about quantifying individual maintenance tasks. I also want to be able to compare complete programs. I want to be able to look at all of the maintenance tasks and say, if we just let them all run to fail, what would be the cost? If we keep doing what we're doing, what's going to be the cost? And what's going to be the cost if I adopt an optimized maintenance strategy? So what we're doing here is we're empowering people to consider alternatives, and we're justifying and quantifying the value of those alternatives so that we can get support for making a change and starting to change away from the concept of this is what we've always done here. This allows you to prove there's other ways that we can do the maintenance, enable you to justify them in a simulated environment. And we also want to do some other things. We want to say, right, where are our exposures? What's the single highest cost failure mode here? This particular one, there's one that stands out here that's a $1.1 million risk to our business. Now, there may not be anything more from a maintenance perspective that I can do here. I can't just do more maintenance because, as we saw on those balance curves, that I've already picked the optimal time to do it. I've already picked the applicable task if there was one. So this is my target for my continuous improvement. This is my root cause analysis, the target that I go after. This is the redesign I go after, and I'm able to quantify the value of what that particular investigation could potentially save me. So it's good to be able to understand this. We could also understand these exposures from a safety, environmental, and operational criticality perspective. If you're trying to drive down your safety risks, this gives you a very clear picture and a quantified picture of what that actually is. We also want to be able to forecast budgets, because a bunch of strategies is great, but we need to make sure we've got enough money, and we need to be able to quantify how much money is this strategy going to cost us, and where is our money actually going? Is it going to breakdowns? Is it going to spare parts? Is it going to inspection activities? So we can see that, and we can forecast what that budget's going to be over the lifetime. The budget's no longer just what it was last year. This budget is actually formed based on the tasks that we're doing and the probability of having to do secondary actions, and also the probability of having corrective activities. So we need to be able to forecast the budget. Now, part of that budget is how many people do I need? So we want to look at that. how much labor do we actually require to do the activities, and how are our people spending their day? Do we have enough people? Do we need more people? Remember, I've justified everything, so if I don't have the people that I need, I can go back and reevaluate my strategy and quantify what the value of an extra person would be to the actual business, so I can start to do all those kind of decisions here, as well as I can look at my spare parts and I can start to have a good conversation with my warehouse and my procurement people about the spares I need to keep, the spares I don't necessarily need to keep, because I understand what my usage is here. I've quantified what the usage of each individual spare is and how it's actually used according to the maintenance strategy that I've adopted here. We also want to continue to improve this, and for people to gain confidence in what you're trying to do here in terms of quantifying maintenance decisions, it's good if we can start using some actual data. Now, I know right now most people are going to say, well, I don't have any data, or I can't do any of this. Well, you still can, because you have some very good knowledge in your employees' heads there that they know how it happens, they know how long it takes to repair, and they know what the effect of failure is if you don't do the right maintenance activity. So draw upon that information, document it here, and document it to drive to that final decision, because without that, you don't really have a starting point for when you do have data to come back and actually evaluate, well, how far was I off with my original assumptions? But you do want to collect data, you want to use it to continually refine your decisions, continually re-quantify what the value of all those different maintenance tasks are. So don't stop collecting that information. So an RCM program as a whole delivers a safe operation, ensures plant reliability and efficiency, provides a documented base for planned maintenance, predicts resource requirements, predicts spares usage, and predicts maintenance budget. And it actually quantifies all of these things. It quantifies the value of maintenance tasks, and that's really what we want to be doing today. So we're going to have a brief question and answer session. I'm going to just pause for a second and review the questions we've had come in this afternoon here, and I'll be right back. So if anybody's got any questions, please complete them in the chat window there, and we'll proceed from there.
So one question we got here is, what data do you use to drive these decisions? And it's an interesting question because you're currently making the decisions today. So we can't just stop and say, we're going to wait till we have much better data to be able to make the decision. We need to make the decision by talking to people in a facilitated environment, going and doing interviews with the guys doing the work, because they have a pretty good understanding of when the failure modes occur and how they resolve it. So those kind of things, we can do that as a starting point, and as we get better data in the future, we can work to leverage that data in the future. So the next question we got here is, does the software integrate with CMMS? It does, and that's a good question, because that's an essential element to ensure you're successful, is to ensure that you're actually integrating with CMMS packages. So we're talking the SAP, the Maximo, the Ellipse, the JD Edwards, all those type of packages. That's where the work is being generated from. What I've shown you today is really the decision-making piece about how often do we need to do the maintenance tasks, but that's a really essential piece to be able to integrate with those systems. And there's a number of different options on how we actually integrate. So we've got another question here. Is there an easy way of doing this without the software? Well, there is. You can do some of this in Excel. I was mentioning a little earlier, you can't do all of the functionality that we've seen here today, but you can definitely do a very basic balance between the cost of maintenance if we did it run to fail, and the cost of maintenance if we did it on a fixed time or inspection basis. It does get a little more complicated when we're trying to introduce the probability of failure into our analysis, but we can do some of it in a simple Excel spreadsheet. So we've got another question here about how much training would be required to get it up and running. Everything I've showed you today is a 3-day training course. So the training isn't a long training course. It's relatively easy to use. The people who are building your strategies today already know all this information. So it's not like they have to look at things a different way. It's just about documenting what they're currently doing. So the software is very easy to learn, it's very intuitive, and it doesn't take long to be able to have people up and running and starting to do some of this decision making that I showed you today. Final question I got is, what's the minimum amount of data needed to run the application and start making these decisions? And it is a scalable solution, but you do need some minimum data. The minimum information we would need is, what's the consequence of failure? What's it going to cost you if we do this in a reactive type environment? What's that downtime cost? Is there any safety risks there? The other piece of information we need is, how often does this happen? And that doesn't have to be actual data out of our CMMS systems. It can be a subjective, how often does this happen? But we at least convert that or translate that to label parameters that the software can actually understand. We then need to look at, what's the maintenance task going to cost? And we can just put that as one value. We don't have to split out the labor and the durations. We can just put, what does it cost to do that? To do both the run to fail, to do the fixed time, and to do the inspection. So those are some of the minimum amount of information we would need to be able to get up and running. So the final question was, is the presentation available for download? Yes, it will be. A link to this recording will be posted on our website, and we will be sending the presentation out to all attendees.
So I think that's the end of the questions. If anyone wants to contact me afterwards, my details are there. Again, I'm Jason Ballantyne, Engineering Manager with North America. My direct phone line there and email address if there is any further questions. As a side note, we do have some public training coming up in how to evaluate these decisions using the tool I showed you there today in late July. So if you'd like to go to our website, www.armsreliability.com, you'll find all information about that particular training course that we have coming up. Thank you for all your attendance in our webinar today, or your registration if you're receiving this via the recording. I look forward to talking to you again in our next webinar.